Welcome to the Petro Papers podcast. Say that 10 times fast. This is where you get your oil and gas intellectual stimulation by asking the technical questions. I'm Yogashri Pradhan, and with me here today, I have Oladapo Adejare from Reservoirs. Today, I am going to talk about ERTEC 372-3724 and ask Oladapo the technical questions, peppering him with the questions based on the paper that he wrote most recently. The paper title and the description is in the description box for viewers and listeners. Welcome to the podcast, Dapo.
Hey, thanks for having me.
I am really excited to start season 3 of Petro Papers, and I'm really glad to kick it off with you.
Honored to be here. You've had some distinguished guests on in the past, so it's a great honor.
Perfect. I wanted to go ahead and just read a little bit about you before I start peppering you with some of the questions. So Dapo is a reservoir engineer for Revo Testing Technologies. He's also been a research engineer for Nalco Champion and focused on well performance modeling. He graduated from Texas A&M University with his Master of Science in Petroleum Engineering, and then the University of Lagos in the Bachelor of Science in Mechanical Engineering. So he also worked as an audit associate for KPMG Nigeria for about a year. So Dapo, I'm really glad to have you on the podcast, and I'm just going to go ahead and get started.
Great, let's do it.
Well, to orient our viewers and listeners, I wanted to ask you, could you briefly describe the paper and the methodology?
So yeah, our objective was to find a way of correlating performance during the initial production period, that's within the first 1 to 2 months of production, with long-term performance. That's 3 to 5 years or until the well is abandoned. So that's what motivated this paper primarily. And the idea is to, on one hand, be able to understand how wells can perform very early on and can get some basis for a more reliable forecast using that initial production data. And the other idea is if we're able to do that, then we can use that as a part of a well surveillance tool for monitoring well's performance through its life, not just during the initial production period. So that was the main motivation. And one of the main challenges that we faced was the non-uniqueness of the analysis, in the sense that there's a wide range of permeabilities and fracture half lengths that we could use to match the data. And so if we wanted to get a consistent interpretation that we can use to compare one well to another, there's a challenge there in terms of finding a permeability that we could use consistently from one well to another. So when we reviewed the literature, we found that there's been publications in the past where the analysts had used radial flow analysis for evaluating performance in low permeability reservoirs. And so what we had to figure out was how to combine that assumption with a way of determining the number of dominant fractures, and then also identifying signatures on the log law plot and a normalized rate cumulative plot that we can use to diagnose early fracture interference. So it was based on just reviewing the literature and then also bringing some additional insights from looking at lots of initial production data from hundreds of wells across multiple basins to see if there were signatures that indicated that even if fractures were not necessarily propagating radially, but at least we're seeing something that looked like interference that we could use as a way of constraining the analysis and determining a unique estimate of the permeability and fracture half length.
Awesome. I was really interested when I read the paper because I know the importance of high resolution data, and I'm going to go ahead and ask you about that later on in the podcast. But I wanted to touch upon what you've mentioned about understanding the number of fractures. What are the implications to early interference between dominant fractures? What should engineers and management be concerned about just based on some of the work that you've done?
So it's not necessarily indicating something that people should be concerned about. It just indicates that it's one more tool in the toolbox that can be used to model and forecast production. And the advantage is that it can be done very early on. And so you can start to get an understanding of how a well is performing relative to another well pretty early on, as opposed to waiting to get more data. Now, in terms of economic optimization, permeability is an important factor. If permeability is higher, then in principle, you should space your clusters more further apart. And if permeability is lower, you'd have to space your clusters more closely in order to drain the reservoir effectively. Now, having said that, even though we're getting a permeability estimate from this analysis, I wouldn't use that alone as a way of optimizing the cluster spacing. I would make sure that I'm combining that information with other diagnostic information and make sure there's some consistency before drawing conclusions about what this analysis might be indicating as to whether the cluster spacing was optimal or not. So the main thing is it's one more tool in the toolbox, and it's indicating that there are signatures that are occurring early in the well's life that can give some additional information that should be considered along with other information in forecasting production and in optimizing completion designs and well spacing. But I wouldn't rely on this on its own to draw those conclusions.
Great. It does take a lot of pieces of data in order to come up with a conclusion or to converge to a certain conclusion. So I'm glad to know. So I'm glad to know this is a part of the engineering toolbox, and I can admit that when looking at some of this data, especially when reading the paper, it seems like it's very useful information.
Yes, indeed. So that's how we like to phrase it. It's one more tool in the toolbox. It's one more way of estimating the permeability. And you should compare this with, if you have defect data, for example, see what the permeability you get from this analysis is and compare with the defect. If you've got information about your perforation friction, how much perforation friction did you have across the clusters in each stage? Was it sufficient to ensure that each stage was taking fluid and proppant? And just tie that back to the number of clusters you're calculating from this analysis and see if there's inconsistency there. Do you have information about, say, isolation between clusters outside of the casing? Is it possible that there's fluid propagating between the cement sheet and the casing and it causing a coalescence of the fractures between different clusters? Or how much stress shadowing do you anticipate can be occurring between the clusters in the formation? So if fractures start to propagate from one cluster, will that prevent fractures from other clusters from propagating? So if you have to integrate all that information into the analysis to see if the results are consistent, and then if they are, then maybe this can lead you to some strong conclusions. But I would not use this information on its own, other than to say that it's one more tool in the toolbox, and you can start applying it really early in the well's life for the first 30 to 60 days.
Absolutely. I wanted to pivot a little bit and talk a little bit about choke management and drawdown strategies, for example. And the paper has talked about advising an engineered choke strategy. And I know a lot of people have different opinions on drawdown strategy, whether to rip it open or use an engineered choke strategy. And there have been many papers that discuss different sides of the spectrum. So I wanted to get your take. Do all reservoirs require an engineered choke strategy?
So my answer would be that an engineered choke strategy I see it as a subset of well surveillance. So basically it's a well surveillance tool. If you can build a well surveillance tool that makes it easy to monitor your well's performance and that can alert you to changes in the well's performance in real time, I like to believe that that's something that every operator would like to have. So from that perspective, from the perspective of well surveillance and automated modeling of well performance to understand how it's changing and to get alerts as to if you start to have a problem with the well's performance. Then I would say if you can automate the process to where it's not time consuming to monitor a large number of wells at the same time, then yes, you should go for it. So I see it more as a general question about well surveillance, and I see choke management as just a smaller subset of well surveillance. And I guess I could turn that question around to you. Working for an operating company, would you like to be able to see how your wells are performing in real time and be able to diagnose problems immediately, as opposed to having to find out a little bit later, and also having to spend a lot of time gathering that information as opposed to having an automated process?
I plead the fifth. No, I just wanted to mention to you. No, you bring up a really good point. I do want to mention that a lot of the thoughts, especially on this podcast, are my own. But
Okay,
but yes, we're working for a company. I would think that having that high resolution data is very important, especially as an engineer. I love data. So upon reading your paper or reading your company's paper, it was very interesting, and it just excited me, which is why I wanted to have you on the podcast. But I would have to admit that having the data to understand what is the right strategy is definitely important.
Yeah, and I've definitely observed a wide range of characteristics. Some wells are suited to faster choke changes, and others are not. And if you can automate the process, it's then easy to identify and understand which strategy works best for which well. And so that's, does every well require that? Well, if you want to calibrate and understand how every well is performing, then the only way to find out is to have a process that's automated that allows you to monitor easily.
Perfect. I wanted to also talk about some elements of the paper. For example, there can be indications of damage from some of the high resolution data. There can be, you can see whether if there's indications of damage or potential damage. Can't you also see that in the diagnostic plots when you're doing the RTA? Because there was some discussion on RTA in the paper as well. Has there been any corroboration with seeing damage in the high resolution data along with seeing skin on in the diagnostic plots?
So yeah, the analysis determines a skin factor, which is converted to a fracture half length. So some of the damage that we see is in the form of a decrease in the fracture half length, which is the skin. And sometimes we also see a combination of a decrease in the fracture half length of skin and the far field transmissibility. So the fracture half length would be a reflection of of damage near the wallbore or in the fractures. And then we also see sometimes a degradation of far field transmissibility, or a combination of the two. So I've seen both occur.
Perfect.
Did I answer a question, or was there
You answered my question. And I guess this is one of those questions that I have in terms of identifying damage, and coming from somebody that works for an operator. Can this damage be repaired? And yeah, can this damage be repaired?
So one thing that I've observed is sometimes there's a what may be best described as a pressure dependent damage. And sometimes when you apply a lot of drawdown, you start to see a decrease in performance. And then when you relax that drawdown, either you choke the wall back a bit or you hold the choke for a little bit longer, you see that damage dissipates. What causes that to happen? I can't say for sure, but typically what would characterize that as if the formation is very is what we consider to be stress sensitive, then it's usually less forgiving in that regard. Meaning that if you've applied so much drawdown to where you start to see a degradation in performance, then there's nothing that can be done to restore that loss of performance. And then there are other formations that are more forgiving, where when you apply a lot of drawdown, you may start to see a degradation in performance. And then when you relax that drawdown, you choke the ball back, you can see the ball recover. And so we don't necessarily know why that happens, but we chalk it down to the degree of stress sensitivity. So it is possible, but it just depends on what would generally term the stress sensitivity of the formation.
Well, thanks for giving me hope, in the sense that there are ways to redeem yourself if there is damage that is identified. Again, I really enjoyed looking at this data, which is why I couldn't wait to talk to you about this, because I had tons of questions.
Excellent.
Well, I wanted to pivot again to fracture interference, because the paper does talk about that.
Yep.
And you've gotten a couple examples from the SP repository.
Mhm.
Now, the SP repository has some older vintage wells that
Yes.
was used for the analysis. So I was curious to know, is there a limit where it would be difficult to tell intercluster or interfracture interference? Because the case studies you show had relatively light completion intensities and compared to the completion designs pumped today in unconventionals. So what if we had like 10 clusters a stage or 20 clusters a stage? Can we still tell the intercluster and interfracture interference?
Yes, that's an excellent question. So for those that may not be familiar with it, the SP data repository is a publicly accessible database with about 50 wells right now from 2, 3, 4 unconventional reservoirs. It's a publicly available database that anyone can go in and download and analyze. So the reason why we chose those data sets is because it would be easier for people to reproduce what we did, because that data is publicly available. So we have applied the analysis to what you'd call Gen 4 completions with very tight cluster spacing, 15 feet, 20 feet between clusters. And I've observed up to say 20 or 30 or 40% cluster efficiency from using this analysis when applied to those wells. So that's indicating, say, 2 out of every 5 or 1 out of every 3 on the low end, 1 out of every 5 clusters is contributing to far field drainage. Now, does that, and going back to what I said earlier, I wouldn't use the values we determine from the analysis on their own as an indication of how effective the frac design was in initiation and propagating fractures, and also as an indication of how closely or widely spaced clusters should be. What I would do, as I said earlier, is to combine that information with other diagnostic information. I see there's inconsistency. It is possible that there may not be, in which case I would, I'm perfectly happy to, to not place a lot of emphasis on the results of the analysis. However, if it is consistent with what's been observed with our diagnostic information, then that could point you in some in a direction as to indicating what the best way forward is to optimize the completions. Now, there have been some instances where we've calculated a very low number of clusters or cluster efficiency. So instead of 20, 30%, using 5%, even though the clusters were spaced very closely. Now, in those instances, one of the things I think is happening is it's possibly indicating that there may be some inconsistencies in the inputs. So for example, I've noticed for some wells with very high water cuts that there's an inconsistency between the contacted volume from flow material balance plot and the petrophysical inputs, which is indicating possibly that either you're assuming the water rates that you're assuming is coming from reservoirs is much higher than the actual rate, or or there's something wrong with the input saturations, or the hyperstage is smaller than the petrophysically derived. The actual hyperstage is much higher than the petrophysically derived value. So when we observe that the number of clusters is low, it is possible that maybe it's something going on with the inputs. The other possibility is, again, if you're able to confirm with the operator, or as an operator, you're able to confirm internally that there may have been something that went on with the completion design that may have reduced the cluster efficiency. So in some instances, we've been able to confirm that the operator did not believe that the isolation on the outside of the casing was very effective. And so it seemed reasonable that fractures would coalesce and you'd have a few dominant fractures as opposed to having many smaller fractures being created. So we have seen some results that don't make sense. We think there may be some physical explanations for that. We do see results that seem reasonable in terms of cluster efficiency, say 20 to 30 or 40% cluster efficiency. And again, I'll just say, okay, this is just one more way of analyzing data, and it's just one more tool in the toolbox. And you should compare it with all the other information to see if it makes sense or not before drawing conclusions.
Thank you.
So yeah, so the question specifically, is there a limit? Possibly, in theory, possibly yes, because one of the assumptions in the analysis is that in order to generate what looks like a radial to radial flow signature, you have to have relatively short effective fracture half lengths, and you also have to have sufficient space between the clusters for that signature to develop. So if there isn't enough space because the clusters are closely spaced and the completion design is very effective in generating fractures from each cluster, then that assumption would not be valid. And so the permeability that you estimate is going to be higher. So it's in that instance, it's going to give you something like a higher limit, an upper limit for your perm should be. And then it's also going to give you a lower limit for your fracture half length should be, if the assumptions for the analysis are not correct or valid.
Thank you for that clarification, Dapo.
You're welcome.
So I had another question for you, and the paper talks about rate transient analysis, and some of the limitations of RTA is the assumption of single phase flow, for instance. And I know in the case study, it was either an oil well, or in the case studies you presented, it was either an oil well or a gas well. Can this analysis be done in multi-phase wells?
Yes, it can. So the gas well was in the Marcellus, so it was effectively dry gas single phase. The oil well was an Eagle Ford well, so it was a multi-phase example actually. So we do take into account the other phases in calculating the, so there's a workflow for calculating the number of fractures, and that workflow, we use the contacted volume at the time at which interference is occurring as indicated by signatures on a log-log plot. And so that volume is actually calculated using all the phases. And I mentioned earlier regarding your last question that sometimes there's some uncertainty introduced because of the water rates. It's especially early on during the flow back before you start to see water oil ratio that's representative of the reservoir. You might underestimate or overestimate that reservoir water rate, and then that could introduce some errors in the contacted volume and the analysis. So we do account for all the phases, and basically what we showed in that paper is the parameters that we determine for an analytical model that we then use to seed the numerical model. So for that Eagle Ford example, I didn't show that, but what I did was to take those parameters and plug it into a numerical model. And then the numerical model has the PVT and the raw perms and all the other good stuff that you can then use to match the multi-phase flow effect. So you'd adjust the PVT as needed and the raw perms as needed to match the gas oil ratio but you see the model with the permeability and fractal health length from that. You see the numerical model with the permeability and fractal health length from the analytical model, because the analytical model was matched using all the phases.
Perfect. That's good to know, because I know there are quite a few people that listen to the podcast. They're actually primarily from the Permian Basin. So having multi-phase effects taken into account of is very important.
Yes, indeed. And we have applied this to, in fact, some of the first wells we applied this to were in the Permian, very high water cut wells.
Yes, exactly. There's one more question I have to ask you, and I can't let you go for this.
Go
But
ahead.
what are some implications of this analysis that we haven't seen before in the industry?
The main implication is we got to, so one of the challenges we had in terms of comparing well performance at the end of flowback is what permeability do we use? So with this workflow, we are able to get a permeability estimate. Now, as I mentioned earlier, take this, it's not necessarily the best or most accurate permeability estimate, but it is a value that we can get consistently and apply across different wells when we're comparing well performance. The other implication is it's an independent estimate of cluster efficiency, as in it's assuming all our assumptions are correct. It does give an indication of the number of clusters that are draining far field away from the wellbore, number of dominant clusters that are draining the reservoir. The third main implication is being able to forecast production right at the end of flowback. What we've observed is that the fractal health length and permeability that we determined, if they don't change significantly, then you can use them quite reliably for a forecast. Now, sometimes we've seen, we do see that there's a deviation from linear flow right at the end of flowback. And so to get a correct forecast, you just have to apply the appropriate fractal dimension using these parameters to get a forecast that matches the data quite well. So, and that's been something we've been trying to do, and I think that many other people in the industry might find value in is you can start to forecast production very early on with this workflow. You can determine parameters very early on with this workflow that you can use for production forecasting. Then the other implication is if you have a model that's reliable and that you can use consistently, you can use it as a basis for monitoring long-term performance. And what we've observed again is we see deviations in this model that coincide with, say, a deviation from linear flow or channel flow. So when this model starts to indicate a decrease in performance, it clearly coincides with the point at which you're seeing a deviation from linear channel flow on the wall flow plot. So in terms of alerting you to those things in real time, if you have this kind of model, it allows you to monitor. Again, as a wall surveillance tool, this can find a lot of practical application. Then the last application I would say that's relatively unique is ranking well performance early on. There's a large number of ways of doing this, but again, the challenge we had was in terms of determining a permeability that we can compare with permeabilities that we're determining from other wells. So we do get a unique estimate of permeability, and so that allows us to rank wells in terms of permeability and fractal health length and number of dominant fractures. So it gives some additional insights as to how wells been performing than other forms of analysis that don't give you a unique estimate of permeability.
Excellent. Well, I'm really glad I asked you that question. Didn't realize there were so many implications, and I could tell from the paper that there were quite a few implications, but thank you for listing them out for us.
I hope they are. I hope people try out the workflow and see if they see the same results and also critique it. We certainly don't think it's. I'm speaking for myself and my co-authors. We don't think it's perfect. As I mentioned earlier, there's some limiting assumptions that may not always apply. And so I think the times when it might fail, but we have found value in it, and we thought we should just share it with everyone and see what other people have to say.
Perfect. Well, thank you so much, Dapo, for letting me pepper you with questions.
Well, thanks, Yoshi. I really appreciate coming on. Like I said earlier, you've had some really distinguished guests, so I'm really honored.
Well, that's a wrap, folks. Thank you for listening to this URTEC paper. And once again, I'd like to thank Dapo for letting me pepper him with questions. If you have a paper that you'd like for me to read and then pepper you with questions, feel free to reach out to me. Our contact information is in the description box below. I'm Yoga Pradhan. This is Petro Papers, and we're signing off.